Let's do one example where we review the delta function. So in here, let's consider the moving delta function well. V of x and t equals to minus alpha, which has units of 1 over length, remember, times the delta function, delta of x minus vt, where v is the velocity, so it has units of meters over second. So now the first thing we need to show is that the time-dependent Schrödinger equation emits the exact solution of this psi, which is made out of this normalization constant here times these two parts, the two exponentials. And here E, the energy in here, is equal to minus m times alpha squared divided by 2h bar. And this is the bound state energy for the stationary delta function, okay? So the second thing we need to show is we need to find the expectation value of the Hamiltonian. So as usual, if we want to show that this solution satisfies the time-dependent Schrödinger equation, we have to first take one time derivative of psi, so d psi dt, and then we have to take first x derivative, and then we have to take second x derivative. So let's start with the time derivative. If you take the time derivative of that wave function from the previous slide, we get minus m alpha divided by h bar square times the time derivative of the absolute value of x minus vt. And what else we have? We have, this is times, we have minus I times E plus mv square over 2 divided by h times psi. So let's here on the side take a look at this piece. So the time derivative of the absolute value of x minus vt, this equals to minus v if x minus vt is positive, and it's v if x minus vt is negative, right? So this piece makes things a little bit more messy, but if you remember from video number 22, we took a look at the step function theta of x, and we defined it to be 1 if x is positive, and it's 0 if x is negative, right? So now we also showed that the time derivative, the x derivative of theta is equal to a delta function. This is video number 22. So from here we can relate to this here in the red, okay, to find 2 times theta of z now, because why not, minus 1, what this is going to equal to. It's going to equal 1 if z is positive, and it's going to equal minus 1 if z is negative, less than 0. Right, so you can see how we're getting close to this equation in the red, because we have minus v and v. So now, if we take one time derivative, so we take one time derivative of the absolute value of x minus vt, and we know this is going to give us minus v times 2 theta minus vt minus 1. Right? Okay, good. So now we can move forward, so let's multiply I h bar times the time derivative of psi, and doing this we get minus mv minus m alpha v divided by h bar times 2 times theta of x minus vt, which is a step function, minus 1 plus e plus mv squared divided by 2 times psi. Okay, keep this in mind. This is, we have another bracket here. This is, I h by times the time derivative of psi. So now let's take one x derivative of psi minus m times alpha divided by h bar square times the x derivative of the absolute value of x minus vt, right, plus I m v divided by h bar times psi. Okay, good. So now let's move forward. We have this piece here. Let's take a look at this piece. What this piece gives us. So the x derivative of absolute value of x minus vt. This should give us 2 times theta of x minus vt minus 1. Do the math. Go ahead and check it for yourself and you'll see how we get that. So now let's simplify this a little bit further. So this is psi of x. So now we have minus m times alpha divided by h bar square times 2 times theta of x minus vt minus 1, close brackets, plus I m v divided by h bar, and of course all of this times psi. Alright, so one more step. Let's take a second derivative of x. So now we have d psi dx squared equals to minus m times alpha divided by h bar square times 2 times this step function theta of x minus vt minus 1 plus I m v divided by h bar, and all of that is square times psi. That's the first part, right? Minus 2m, remember the product rule, times alpha divided by h bar square times the x derivative of theta times x minus vt. Now this becomes very handy. I mean, video number 22. Of course, that's times psi. Why? Because in video number 2 we showed this gonna give us the delta function, of whatever we are dealing with, which is x minus vt. Alright, so now let's simplify this a little bit further. So we have minus h bar square divided by 2m times the second derivative of psi with respect to x minus alpha times the delta function x minus vt times psi. So what this is gonna give us? This should give us the time derivative, right? So let's substitute this technically should be equal to, here let me put it in this color, it should be equal to I h bar times the psi derivative, I mean the time derivative of psi, right? But we don't clearly see that, so let's simplify this a little bit further. So we have, put back this color, so open parentheses, we have minus h bar squared divided by 2m times curly bracket. Let's substitute this second derivative, which we have minus m alpha divided by h bar squared times this weird term 2 times theta of x minus vt minus 1, right, plus I m v divided by h bar square, and this is being squared, right, plus, we're not done, plus this, so we have plus alpha times canonical delta of x minus v t minus, let's put it over here, alpha times canonical delta of x minus vt. I hope you see where these two came from. Close parentheses times psi. Let's simplify this a little bit further. So now we have equal minus ih bar squared divided by 2m times m squared alpha squared divided by h bar to the fourth. You see where this is coming from, right? Times 2 times the step function theta of x minus vt minus 1 square minus the cross terms, so we have m squared v squared divided by h bar squared minus, oh no, these are this is the second term. Now the cross terms, we have 2 times I times m v divided by h bar times m alpha divided by h bar square, or alpha m, times 2 times the step function theta of x minus vt minus 1 close curly bracket times psi. Simplify a little bit further. This gives us minus m alpha squared divided by 2 h bar squared plus 1/2 mv squared, kinetic energy, right? mv squared plus I times mv times alpha divided by h bar times 2 times theta of x minus vt minus 1 and curly brackets times psi. And if you check this from earlier slides, just compare it, this is going to be equal to I h bar times the time derivative of psi. There you have it. So now let's just move forward to part B, where we have to find the expectation value of the Hamiltonian. So first let's find the probability density. So psi star psi, so this is equal to m times alpha divided by h bar square times the times e to the minus 2m alpha times absolute value of y divided by h bar square. And as usual, we have to define y. In this case, y is defined as x minus vt. So remember, y has units of meters. Let's check normalization. So we have 2, this is a constant, times m alpha divided by h bar square. Let's integrate from 0 to infinity of e to the minus, remember the integral over all space of the probability density must equal 1. So let's check that. M times alpha divided times y divided by h bar square times dy. dy is just dx. So this is equal to m times alpha, 2m times alpha divided by h bar square, and this integral is going to equal to h bar square divided by 2m alpha, and indeed this is equal to 1. So that's good. So now we have the expectation value of the Hamiltonian, which means we have to sandwich this Hamiltonian between psi star psi and integrate over all space. So now, so we have psi star and then h times psi dx. But what do we know? We know that in this case h times psi is equal to I h bar times the time derivative of psi. Well, not in this case, in any case, right? So, which is calculated above. So this here, we have it above. So let's simplify it a little bit further. So this is going to equal to the integral of I m times alpha times v divided by h bar times 2 of the step function y theta of y minus 1 brackets plus e plus 1/2 m v square. So this is here times the probability density psi star psi dy. And if you do this, let's take a look at this. This is the first part is okay. First of all, this integral, let me put it in red. This here, we know it's 1, right? We did it above here, and this integral must be 0. The Kronecker delta integral, right? It kills everything, so it must be 0. So we left with these two. So the expectation value of the Hamiltonian is equal to E plus 1/2 mv square. Note that let's talk a little bit about this previous slide here, the Kronecker delta integral. Note that 2 times theta of y minus 1 is an odd function of y, so this is odd function of y. That's why it's 0. Let's comment at the result here. So the wave packet is dragged along at speed of v, right, with the delta function. The total energy is the energy it would have in the stationary delta function, we did it earlier, plus the kinetic energy due to the motion. So that's what this thing means. So the stationary, the total energy is the energy made out of the stationary delta function plus the kinetic energy of the motion.